In this video, I'm going to analyze the function f of x equals 2x divided by x squared minus 4. We're going to use that original function formula to identify the domain, whether there are any asymptotes, and the x and y intercepts. Because it's a rational function, the domain will be restricted when the denominator x squared minus 4 equals 0. Solving this equation, we see that x would equal positive 2 or negative 2, and we can't allow that to happen. So we could express the domain in two ways. We could say x can't equal 2 and x can't equal negative 2. Or using interval notation, we could say what x is. The values of x that are acceptable are from negative infinity up to negative 2, from negative 2 to 2, and then from 2 to infinity. Vertical asymptotes happen when the denominator equals 0 and the top doesn't. So I can see that there are vertical asymptotes when x equals 2 and when x equals negative 2. So those vertical lines will be asymptotes. Horizontal asymptotes, in this case we get a horizontal asymptote of y equals 0 because the degree of the denominator is larger than the degree of the numerator. The denominator is degree 2 and the numerator is degree 1. Finally, the intercepts. To find y-intercepts, we can set x equal to 0, and if we do that, we get y equals 2 times 0 divided by 0 minus 4, which equals 0. But that also tells us then that the x-intercept, which occurs when we set y equal to 0, is also going to be 0. So there's only one intercept, 0, 0. To identify when the function is increasing or decreasing, we're going to use the first derivative. To find the first derivative, we need the quotient rule. I'm going to take the derivative of the top times the bottom minus the top as it is times the derivative of the bottom, divided by the denominator squared. So we can simplify this a little bit. The numerator becomes 2x squared minus 8 minus 4x squared. And we can simplify that a little bit further. Combining like terms, we get negative 2x squared minus 8 divided by x squared minus 4 squared. And let me do one last thing. I'm going to factor out a negative 2, which will help us see that the numerator can never be equal to 0, because x squared plus 4 will never equal 0. X squared is always a non-negative value, and so if I add 4 to that, this numerator will always be positive. So this is always positive. So what that means, the information we need to know, in order to analyze when the function is increasing or decreasing, I want to find the critical numbers. And in this case, there's no place where the derivative equals 0, because of what I just mentioned. The numerator never equals 0. So this never happens, but the derivative does not exist when x equals 2 and when x equals negative 2. For the same reason, the original function doesn't exist. The denominator becomes 0 for those points. So we can create a sign chart for the first derivative. Negative 2 and 0 are the only two critical points. I can put, not defined here. And then I can choose some test points, negative 10, 0, and 10. And think about the value of this expression. So for a value like negative 10, the top of the derivative is going to be negative, and the bottom is going to be positive. So it's negative overall. For 0, the top is going to be negative, the bottom is going to be positive, because we're squaring the denominator, so actually the denominator will always be positive. And because of the minus 2 in front, the numerator will always be negative. So for this function, the graph is always decreasing. So there are no local extrema. So we've covered the second two things for us to investigate. We've identified that the function is always decreasing where it's defined. So I guess to write that out, I could say it's decreasing on its domain, which is negative infinity to negative 2, negative 2 to 0 to 2, and 2 to infinity. And because of that, there are no local extrema. It never switches from negative to positive, like at a point where the function is defined. So finally, we're going to look at the second derivative to analyze concavity. So let me write the simplified form of the first derivative down here. We found it to be, let me write this version, negative 2x squared minus 8 divided by x squared minus 4 squared. So the second derivative, we're going to again use the quotient rule. The derivative of the numerator is negative 4x times the denominator. And then I want to subtract the numerator as it is, which I can factor out that negative to create a plus 2x squared plus 8. And then times the derivative of the denominator, which is 2, x squared minus 4. Using the power rule, we can bring the 2 to the front. Leave the inside alone for a moment, but then I need to multiply by the derivative of the inside, so I need to multiply by 2x. So that's the numerator of the second derivative. The denominator is going to be x squared minus 4 to the 4th power, because I'm squaring the square down here. And x squared minus 4 squared and then squared, I can multiply those exponents, and we get x squared minus 4 to the 4th. So let's try to simplify this a little bit before we analyze the result. Notice that there is a factor of x squared minus 4 on both sides of this big plus sign. And so I can factor that to the front, and it will actually cancel with the denominator. So I'm going to factor out x squared minus 4. It leaves behind negative 4x times x squared minus 4. And then the plus sign up here is the same as the plus sign there. And the second group, we took away the entire x squared plus 4, so the second group has a 2x squared plus 8 times 4x. The 2 here times the 2x there. So these can now cancel, and I just have 3 x squared minus 4's down there, so x squared minus 4 to the third power. And we can simplify the numerator a little bit. So I get negative 4x to the third power plus 16, and then plus 8x squared, nope, 8x to the third power plus 32x. And finally, combining like terms, I get 4x to the third power. And sorry about that, there should be an x from here next to this 16. So I get negative 4x cubed and positive 8x cubed gives me negative 4x cubed. And then positive 16x and positive 32x becomes 48x divided by x squared minus 4 cubed. So the second derivative does not exist for the same 2 points. So the second derivative does not exist when x equals 2 or negative 2. But we also get a value where the second derivative equals 0. This is going to happen when the numerator equals 0, so 4x cubed plus 48x. And because both terms have a factor of 4x, we see that the second derivative will equal 0 when x equals 0. But it doesn't have any additional factors. It doesn't have any additional partition points, because this other factor will never be 0, will never equal 0 for the same reason that we saw earlier. X squared is always non-negative, and adding 16 will always then make that positive. So I'm going to organize my work up here for the second derivative. Let me make a sign chart, this time for the second derivative. And this time I need to mark negative 2, 0, and positive 2. And looking at our formula for the second derivative, the simplified formula here, and actually if we make the numerator 4x times x squared plus 16, it becomes even easier to see that for a value like negative 10, the top is going to be negative, and the denominator, because the x squared becomes the larger piece, the denominator is going to be positive. So we see a negative value overall. The function is going to be concave down. Then remember, the value is not defined here, but it's equal to 0, the second derivative function, it's equal to 0 at 0. So for a test point like -1, the numerator is still going to be negative, but this time the -4 term becomes sort of the bigger term. So the denominator is also negative, so it's positive overall. So it's concave up. When we cross over 0, the numerator now is positive and the denominator is negative. So it's negative overall and concave down. And finally, for a value like 10, the top and the bottom are both positive. So it's concave up. And so creating a sketch, I haven't given myself very much space for the sketch. I know that the graph is concave up. I guess let me summarize this. It's concave up on the interval from -2 to 0 and from 2 to infinity. And it's concave down on the interval -infinity to -2 and 0 to 2. Because it's undefined, because the second derivative is undefined at 2 and -2, those 2 points are not inflection points, but it is defined at 0, and so there is an inflection point at 0, 0. And so, what we've been waiting for, our sketch of the function. I want to add vertical asymptote, so a dashed line for x equals 2, and I'm going to add a dashed line for x equals -2. And going back to the function here, the original function, I guess one thing that we didn't discuss, the function values are going to be negative when x is less than -2, and then they're going to be positive when x is between -2 and 0, because in that case we get a negative value over a negative value. So they'll be up here. And then they'll be negative again when we're between 1 and 2, because in that case, between 1 and 2, the top is positive, but the bottom is still negative. And then finally, after 2, it'll be positive again, because both the top and the bottom will be positive. So, understanding what the sign of the original function looks like, my graph is going to be negative here, decreasing and concave down. It's going to be positive here. The x and y intercept are at 0, positive, decreasing, and concave up. But then the inflection point, it now switches to concave down. And finally, the last part is decreasing, of course, it's decreasing everywhere, and concave up. So just to summarize, initially the function is always decreasing where it's defined. To the left of -2, it's concave down and decreasing. Between -2 and 0, the function is positive, concave up and decreasing. And then after 0, it switches to concave down and becomes negative. And then above 2, the function is positive, concave up and decreasing. I hope you enjoyed the video. Thanks for watching.